This tool is one of the simpler features of DNA Center, but also one of the most powerful and commonly used. Let's utilize it to collect information from our sandbox devices. Let's jump straight into our first script named runcommands.py. In this script, we aren't loading data from a JSON file, but rather from a string returned by DNA Center. As usual, we'll use OS to create a directory containing output files and the DNA Center SDK to simplify interaction with our sandbox instance. Let's explore the main function next. Let's build the DNAC object to interface with DNA Center as we always do. We then need to identify the devices in scope for command collection. There are many search parameters available per the documentation, such as IP address, location, and serial number, but we'll keep it simple. Let's look for all Catalyst 9300 switches by specifying a family and a type. These are query parameters appended to the network device resource, so let's issue a GET request to collect a subset of our inventory devices. Next, we must extract the device UUIDs, which is how the command runner identifies the devices to test. The response from the Get Devices request looks like this, where the response key contains a list of dictionaries as its value. If any of these devices specifies an error code, let's skip it because there's a good chance the command runner won't be able to log in. If there isn't an error, let's add the device UUID to a list for consumption later, along with a status message indicating what happened. There are two keys in the HTTP body dictionary. The commands key identifies the exact CLI commands to run on each device, and I've hard-coded a few commands here to illustrate the point. Feel free to move this functionality to a JSON file if you want to build a more modular solution on your own. Notice that I've included a bogus command. We expect the command runner to gracefully handle this invalid case. The second key includes the list of device UUIDs upon which these commands should be run. We'll substitute in the list we assembled a moment ago. Then, we issue an HTTP post request to the read request resource and include the HTTP body we just reviewed. The command runner may take some time, so this is an asynchronous operation. Let's wait for the task to finish and return the results, which are included in the run task variable. Here's a callout showing the structure, and notice the progress key. It's JSON data wrapped in a string, and the topmost key is file ID. Personally, I think this is kind of sloppy, but using json.loads and basic dictionary indexing, we can extract the file ID for follow-on requests. Once we have it, let's issue a GET request to the file resource, including the specific file ID in the URL. This is a JSON representation of the data we collected, and here's what the basic structure looks like. It's a list of dictionaries like many other DNA Center responses. Next, we'll store this data in the command outputs directory, which we must create if it doesn't already exist. Then, we iterate over the list and store the UUID of each device. This will serve as part of the file name on disk, which guarantees uniqueness. Next, let's unpack the nested command responses dictionary for iteration by separating the result text from the command details. We also need to unpack the command text from its output in another loop to dig deeper into the structure. The result can be success, failure, or blacklisted, which we'll print to the console along with the device UUID and command string. Before writing the output text to a file, I like to replace spaces with underscores to keep the file names a bit cleaner, but that isn't technically necessary. Then, we'll create a new file in the output directory, and its name will consist of the UUID followed by the command executed. Last, we'll write the CLI output from the device into the file as plain text. Let me clear the screen before continuing. Let's run the script using the Python command shown, then explore the console output and artifacts. The script discovered two Catalyst 9300 switches named Leaf1 and Leaf2 within the sandbox, and it displays their device IDs. Then, using a series of for loops, our script checks the status of each command on each device. The show version and show inventory commands succeeded on both devices, but show bad stuff failed as expected. Let's look inside the new command outputs directory. This is where each file is saved, consisting of the device ID and command output. Let's explore all the files from Leaf 1, which begin with B8. First, we see the bad stuff file, and the command runner intelligently returns the exact CLI output from the device. DNA Center didn't crash, and the API didn't return an error, which is nice. Next, we see the device inventory, which was a valid command. This reveals the serial number and other hardware-specific details. Last, we see the version information. This is a long file, but we can clearly see the iOS XE software version at the top. Coming up next, let's learn how to troubleshoot complex routing and forwarding problems lurking in our network.